Section 5.1 Exponent Rules. In this section we're going to look at something that should be review, whether you took Math 0305 you would have seen this, or placing into Math 0306 you're expected to already have a decent idea of these exponent rules, but at least in these videos I'll kind of go through all the basics. First of all, exponents. What is an exponent? We talk about writing something in exponential notation, which is what we have these first two expressions in. We have a base, which is the large either variable or number that is that we are raising an exponent to, and the exponent or power is the small number that we have raised. And what it means is x to the second power. It's telling us how many times we are raising that base, or how many times we are multiplying, how many factors of that base we have. So x squared, or x to the second power, would mean we have two factors of x, which means we're multiplying x times itself twice. 5 to the fourth power would mean we have four factors of 5. So 5 times 5 times 5 times 5. So we can turn exponential form and just write it as repeated multiplication. Of course, it's a little bit shorter to write in exponential form, and that's usually why we do that. So then we talk about some of these different rules that apply when you're dealing with different operations involving exponents. Some involving variables as your base, like what we have with x squared. Some involving numbers as your base, like 5 to the fourth. So first we can look at what we call the product rule. This is the rule when you are multiplying two things that have the same base. When you have two expressions you're multiplying that have that same base. Like down here where we both have, this first example has 2's, that both have base 2's, or down here the bottom example they both have base y. We can apply this product rule. And the way this rule works, if you actually think about these problems as repeated multiplication, if we had 2 to the third power, or 2 to the second power times 2 to the third power, that's actually going to get us 2 factors of 2 times 3 more factors of 2, which ends up adding together to give us 5 factors of 2, or 2 to the fifth. And that kind of develops our first exponent rule, is that when we're multiplying two expressions with the same base, we just add the exponents. So x to the a power times x to the b power, this is how we write kind of the general rule, is going to be the same base x, and we would add the two powers, the exponents. So in our examples here we'd have 2 to the fifth power, y to the fifth times y to the eighth would give us y to the 13th power. Okay, so that's the basic application of the product rule. Whereas over here we have a more difficult application. Maybe doesn't look exactly like it, but it still applies. So multiplying these two expressions, which is what we would have to do because we have no operation in between the two parentheses, which implies multiplication. So we would be expected to multiply the two expressions, and how we can break this down is looking at the two. We can multiply our two coefficients, the -3 and the 4. We can look at the x terms, the x factors being multiplied together, and the y factors. So in your head, although you don't necessarily have to write this step out, this is what should be going on. We're multiplying -3 times the 4, the coefficients out front. We're going to be combining the x pieces, x squared times x to the fifth, and then y to the fourth times y to the sixth. So for now I would write that step down. Maybe you're good enough you don't need to write that step down, but at least that's what should be going on in your head. So -3 times 4 gives us -12. And now because we are multiplying things with the same base, we would just add our x exponents and add our y exponents. So we would get x to the 7th and y to the 10th. Okay. Next we have what is called the quotient rule. This is going to be when we're not multiplying things with the same base, but dividing them. So if you remember the rule, when you're multiplying things with the same base, we added the exponents. If we're dividing things with the same base, we subtract the exponents. In other words, we kind of cancel out factors. So if we had something like x to the a power over x to the b power, Well, it's going to combine to keep that same base x, and we would just subtract the powers a minus b. So in an example here, we have 7 to the 16th power over 7 to the 10th power. If you wanted to write that out as repeated multiplication, we could. The numerator would be 7 times 7 times 7 until we saw 16 factors of 7 across the top. The denominator would be 10 factors of 7 across the bottom. What would end up happening is we could cancel out factors, and if we canceled out 10 from the top and 10 from the bottom, we'd be left with 6 up top. But rather than having to write that all out, it'd be the same thing if we just subtracted 16 minus 10. So this is going to be 10 to the 16, or 7 to the 16 minus 10 power, which would just leave us with 7 to the 6th power. And in that example, I'm just going to keep it in exponential form. We then, of course, if we wanted to, could multiply 7 times 7 times 7 times 7 times 7 until we saw, multiply 7 times itself, 6 factors of 7. But for now, I'm just going to keep that in exponential. So now a more difficult example, applying the quotient rule. We'll get this over here. 10a to the 9th, b to the 5th, divided by, or over, 2a to the 6th, b. So we can apply the quotient rule here, and once again we can split up what we have. We can think of the 10 over 2 as its own separate fraction, the coefficients. We can think of the a to the 9th over a to the 6th as its own separate fraction and simplify there. And then we have b to the 5th over b. And it is important here to keep in mind, even though the b doesn't have an exponent, technically we do, a single b means we have one factor of b. There's almost like a hidden exponent of 1 there. So simplifying this expression now, 10 divided by 2 gives us 5. Now we're dividing the expressions, so we would subtract the exponents. If we took away 6 factors of 9, or 6 factors of a away from the top, we would be left with 3. 9 minus 6 gives us a to the 3rd. And then if we took 1 factor of b away from the top, 5 minus 1 would give us b to the 4th. Okay? So quotient rule, we're subtracting. We should put a little note of that. Where's up above? Product rule. We add the exponent. Okay. Next rule we're going to look at is the 0 rule. And that is, if we have any number or variable raised to the 0 power, it equals 1. So if we have the variable x raised to the 0 power, that would just be equivalent to 1. 2 to the 0 power, that equals to 1. 99 to the 0 power could be negative 157. If it's raised to the 0 power, it's equivalent to 1. Okay. So on the next page, we'll actually apply a more difficult example of the 0 power rule. Okay. So we have this expression. Because the entire expression is in parentheses and it's being raised to the 0 power, then it actually equals 1. That's a little bit easier than some of these other examples, but the entire value is in the parentheses. It's being raised to the 0 power, so that's going to equal 1. Okay. The bottom example, 5a squared c to the 0, is different. It's not the whole expression that's being raised to the 0 power, it's just the c factor. So just the c factor to the 0 power is what would equal 1. So we could rewrite our expression as 5a squared times 1, because that c portion of the expression being raised to the 0 power just equals 1. So then 5a squared times 1 is just like anything times 1, it just equals itself. So that would remain 5a squared. So you see the two kind of possibilities, the two kind of ways that you could be presented a problem involving the zero product property, or the zero power property, the zero rule. Okay. Our next rule is the power rule. What if we have something raised to an exponent and then that's raised to another exponent? Okay, we have a power, or sometimes we call this the power to a power rule. Well, before even looking at the notes, we could kind of think about something like 3 to the 4th to the 3rd power, or here, maybe I'll even come up here. What if we have something like 2 to the 3rd power, and then we're taking that to the 2nd power? Well, 2 to the 3rd power would mean 2 times 2 times 2, 3 factors of 2. So inside the parentheses, if we took 2 to the 3rd power, it would be 2 times 2 times 2. But then squaring that, taking something to the 2nd power, means repeat it twice. So everything that's in the parenthesis we should see written 2 times. So inside the parenthesis we had 2 times 2 times 2. But then we'd want another parenthesis of 2 times 2 times 2. And you see we end up getting 6 factors of 2. So that's equivalent of saying 2 to the 6th power. How do we get to that power of 6? We could have just done 3 times 2. Okay, because however many factors you have on the inside of the parenthesis will give you that. And then you're going to be multiplying it by however many times we have the power on the outside of the parenthesis. So 3 factors of 2, written twice, is going to give us 6 factors of 2. So the rule here is when you have a power to a power, we multiply the exponents. So x to the a power raised to the b power is going to just be x to the a times b power. We keep that base and multiply the exponents. So just kind of doing the next 2 examples quickly, knowing the rule, we could just multiply our exponents. So 3 to the 4th power to the 3rd power would just be 3 to the 12th power. And x to the 3rd power to the 5th power, multiplying 3 times 5, we get x to the 15th power. Okay. So a little more difficult example, applying that rule over here. We have 3a to the 5th, b to the 4th, and that whole expression is in the parenthesis and being squared, being raised to the 2nd power. So we want to apply this rule. We haven't exactly talked about everything yet, but I'll just kind of mention it. Every factor inside the numerator has to be raised to that power that's outside the numerator. So since that power of 2 is touching the parenthesis, it has to be applied to everything inside. So that's going to give us a 3. We don't need a parenthesis for that. A 3 we're raising to the 2nd power. An a to the 5th that we're raising to the 2nd power. And a b to the 4th that we're raising to the 2nd power. And once you get good at recognizing these kind of problems, you don't necessarily, again, have to write this step, because now we see, well, 3 to the 2nd power, that's just a regular exponent. We have to do 3 times 3, which would give us 9. But in these other 2 factors, the a and the b, we're getting a power to a power, power to a power. That's where we apply the rule and multiply exponents. So that's going to give us a to the 10th when we multiply 5 times 2, and b to the 8th when we multiply 4 times 2. So our final expression would be 9a to the 10th, b to the 8th. Okay. Alright, next we have the product and quotient to a power rule. It's actually kind of what we just talked about. I guess we jumped the gun a little bit. It's pretty much when you have a product, so multiplying 2 things, or a quotient dividing 2 things, or a fraction, inside a parenthesis, and then you're raising that parenthesis to a power. We have to take each factor inside the parenthesis to that power. So kind of like we did over here, we raised the 3 to the 2nd power, the a to the 5th to the 2nd, and the b to the 4th we took to the 2nd. So we kind of already jumped the gun over here doing that example. So if we had xy, that's a product, x times y, being raised to the a power, that's equivalent to taking x to the a power and then multiplying that times y to the a power. Or if we had a fraction, x over y being raised to the a power, that's equivalent to taking x to the a power over y to the a power. We apply that power on the outside of the parenthesis to every factor inside. So our example here, we have 3k in parentheses to the third power. We can break this down into taking 3 to the third power and then taking the single k to the third power. And multiplying that out, we get, well, 3 times 3 times 3. We could take that to 27 if we wanted to. And then k to the third power we could just keep as k to the third. Okay. Whereas in the second example we have a fraction, so we'd have to take everything in that fraction, every factor, because it's inside the parentheses and being raised to the second power, we have to take each factor to the second power. So we'd end up with having to square the 4, having to take the m and square it, all over having to take the n and squaring it. And you normally just want to simplify if you can. 4 squared means 4 times 4, so that'll give you 16m squared over n squared. Okay. So now a little bit, another kind of difficult example using that power, that product or quotient to a power rule, is this. Similar to the one we just did, we have a fraction in parentheses being raised to the second power. So we have to take everything inside that parentheses and raise it to that power of 2. Every factor has to be raised to the power of 2. So this means in the numerator we're going to have a negative 5 to the second power. We're going to have an x to the 4th to the second power. And we're going to have a y to the 6th to the second power. Simplifying all that, negative 5 squared is going to be negative 5 times negative 5, which would give us 25. Now we have a power to a power, so we multiply 4 times 2, gives us x to the 8th. And then we multiply 6 times 2 for the denominator, giving us y to the 12th. So 25x to the 8th, y to the 12th, over y to the 12th. Okay. Then our last rule is the negative exponent rule. And that tells us when we raise a base to a negative exponent, we have to take the reciprocal. We have to flip what we have and make that exponent positive. So in order to turn a negative exponent to a positive, we have to flip what we have. We have to flip the expression, take the reciprocal. Or if we, I guess it's not always that we take the reciprocal. It's pretty much that the factor, the base, whatever has the negative exponent attached to it, that has to move. So in this first example, we don't have a fraction. We could think of this as a fraction by putting it over 1, x to the negative 5th over 1, which then tells us what we can do is flip that fraction, take the reciprocal 1 over x, and now instead of to the negative 5th power, we can write it as a positive 5 power. And we can never, in math, we always want to write our final answers with a positive exponent. So that is what you would have to do in a problem if you got to that point. In our next example, a little bit different. We do have the y to the negative 2 power, but only that is the piece that has to move, because only that has a negative 2, or has a negative exponent attached. So we would take the y to the negative 2 piece and have to move it up. So this is going to equal 3, which would stay up top. We bring the y up top with it, make it a positive 2, and have to put it over 1 for the reciprocal, but anything over 1 is just itself, so we really don't need a fraction anymore. We don't need to write a fraction over 1, we can just keep it as 3y squared. Okay? So that is all of the exponent rules we need to learn. We do have a couple more examples, I think, involving all of the rules inside and out. So we have two more examples here. Well, I guess all the following examples have involve the negative exponents, so we can take a look at finishing these three. So I guess the one thing I would say to try to remember for all of these is that we want to only move the factors with negative exponents. When we do have negative exponents, only move the factors with negative exponents. Alright. So in that first example, 22m to the negative 3, n to the 7th over p to the negative 8, we only want to move the factors with the negative exponents. So that's going to be the m to the negative 3, that piece has to come down, and the p to the negative 8, that piece has to come up. And once we move those pieces, then we can write them as positive exponents. So we're going to get 22 stays up top. We usually write things in alphabetical order, so the n would come next. That remains an n to the positive 7. And now we brought the p up, but now we write it as a positive 8 exponent. And the only piece that's down below now is the m factor. We just moved down into the denominator, and that's going to be m to the 3rd power. Okay. The next example really is just going to require us to, since we have a fraction raised to a negative exponent, in order to make that exponent be positive, we again have to take the reciprocal. So what that's going to look like is we have to flip the fraction. So we ended up flipping the fraction, turning it into b over a, and then that turns it to a positive 2 exponent. Our next step, though, then we would have to apply that power of 2 to each factor inside. So that's going to equal b squared over a squared. And that would be our final result in that problem. We couldn't do the quotient rule where we subtract the exponents because we have different bases here now, b and a. Just like over here we couldn't use the quotient rule because we have different bases, n, p, and m. Okay? So using that idea of flipping the fraction when we had the negative exponent on the outside, we could do that same thing over here for our next example. If we want to rewrite that as a positive 2 exponent, we'd have to flip the entire fraction that we have to begin with in the picture there. So I would probably suggest starting with that. Let's flip it. So doing so, we would end up having 15a to the 3rd, b to the negative 5. And then we don't change that to a positive yet, because all we're doing is what's going to make this exponent change to a positive. Then 5a to the negative 5, and b to the 7th. So then from here, from here, now that we flipped it, we want to take it to the power of 2, positive power. We could now start taking that power of 2 and applying it to each factor inside the parenthesis, the 15a and the b, the 5, the a, and the b here. However, I would move around our negative exponents first. So this b to the negative 5 piece here needs to come down to the bottom. This a to the negative 5 piece needs to come up to the top. Okay? So when we do that, the next line here we have a 15 a to the 3rd, but now we brought the a to the negative 5 up, and it's going to become an a to the positive 5. And down below we had a 5b to the 7th, but we brought this b down below, which is going to be a b to the positive 5 now, because we're making that negative a positive 5 since we moved it.